Quasi-hereditary algebras, lecture 17, generalizations, cellular algebras. Let K be a field. Let A be a finite-dimensional associative and unital K algebra. Definition: a cell datum for A is a tuple which consists of a finite partially ordered set lambda, an anti-automorphism iota of A, for each lambda and lambda a finite set M of lambda, and an injective map C from the disjoint union over all lambda in lambda, M of lambda times M of lambda, to A. Given a cell datum lambda, iota, M and C for A, an algebra A is called cellular, provided that the axioms on the next slide are satisfied. Axiom 1. The image of C should be a basis of A. Notation: we denote by capital C upper lambda lower s comma t the image of C applied to the pair s comma t from m lambda times m lambda. Axiom 2. Iota of C upper lambda lower s comma t should be equal to C upper lambda lower t comma s for all s, t, and lambda. A piece of notation: for little lambda from capital lambda, we denote by A upper less than lambda the linear span in A of all basis elements of the form C upper mu s comma t, where mu is less than lambda. So this should be the linear span of all such elements for all mu and for all relevant s and t. And the final axiom C3. For any element A in A, and for all s, t, and lambda, multiplying A with capital C upper lambda s comma t gives a linear combination over all u in m lambda, some coefficient which we denote by r sub A, u comma s, then the basis element C upper lambda u comma t, modulo A upper less than lambda. And here the main point of the axiom, that the coefficient RAUS should not depend on t at all. So this definition is taken from the original paper by Graham and Lehrer, which is called Cellular Algebras and which appeared in 1996. Here is an example. We claim that the matrix algebra, the algebra of all n times n matrices over K, is cellular. Denote by Eij the usual matrix unit. So here I and j are elements between 1 and n, and Eij is a matrix where we have 1 in position I, j and 0 everywhere else. Let us take as lambda just some singleton set. And let us take as the anti-isomorphism iota the transposition of the matrix. So define M evaluated at our unique element of our set just as a set 1, 2, and so on n, and take the corresponding basis element Cij to be the matrix unit Eij. Of course, if we transpose Eij, we get Eji. So the first two conditions in the definition of a cellular algebra are obviously satisfied. And for the third condition, if we have any matrix M with coefficients MAB, and we multiply M with the matrix unit Eij, the outcome is the sum over S. We take the element little m with indices S and I, so that's an element in our matrix M, and we multiply it with the matrix unit ESJ. And we note that this element little m s comma I does not depend on J. So that's the point of the third axiom of the cellular algebra. Here is another example. Consider the truncated polynomial algebra K of x modulo the ideal generated by x to the power n. Let us take as our finite partially ordered set lambda the set consisting of the elements n-1, n-2, and so on 0 with respect to the opposite natural order. So n-1 is the minimal element, then n-2 and so on, and 0 is the maximal element. So this is a linearly ordered set. Let us take as iota the identity map. Our algebra is commutative, so the identity map is an anti-automorphism. For each I in lambda, we take M of I to be a singleton set consisting of 1. And also for each I in lambda, we take the corresponding basis element C upper I 1, 1 to be x to the power I. And then, of course, the first two axioms are obviously satisfied. And for the third axiom, if we take an arbitrary element f of x in our algebra, we can write it as a sum over s from 0 to n-1, some coefficient a sub s times x to the power s. And if we multiply this with x to the power I, the outcome will be a0 times x to the power I modulo x to the power I plus 1 and the ideal generated by this element. And this implies that the third axiom is also obviously satisfied. So we have a cellular algebra in this case as well. So cellular algebras are good because they come equipped with a collection of modules which are called cell modules. So let A be a cellular algebra with a fixed cell datum lambda, iota, m, and c. For lambda in lambda, consider a vector space which we denote by W of lambda with bases indexed by elements in m lambda. So the basis is capital C sub s, where s is an element of m lambda. And now for A in A and S in m lambda, define the action of this A on our vector space W of lambda as follows. A times the basis element C sub s is a sum, just the usual sum, not a direct sum, the usual sum over all u of m of lambda, and then the basis element Cu with the coefficient r sub a u comma s. That's the same coefficient which appears in the third axiom of the cellular algebra. Lemma, this defines on W of lambda the structure of an A module. And this is clear because we can immediately see from the definition and from the third axiom of the cellular algebra that W of lambda is isomorphic to the quotient of the left A module generated by C upper lambda r comma t modulo A upper less than lambda. And of course, this doesn't depend on t at all. And this module W lambda is called the cell module, which corresponds to the element lambda in lambda. So our algebra A is equipped with a collection of A modules, which are these cell modules W of lambda. These modules also come equipped with a certain bilinear form on them. So for lambda and I, j, s, and t in m lambda, we have that multiplying C upper lambda is with C upper lambda tj outputs C upper lambda I comma j times some coefficient which depends on s and t and which we denote by psi of s and t. And of course this happens modulo A upper less than lambda. So this follows directly from the third axiom of the cellular algebra. And this induces a canonical bilinear form on W of lambda, which we can define as follows. So we denote this canonical bilinear form by phi upper lambda, and when we evaluate it at the basis elements Cs and Ct, we declare that the outcome is exactly this coefficient psi of s comma t. For example, if we go back to our example of the matrix algebra as a cell algebra, then the cell basis of this algebra consists of matrix units, and the cell module, which corresponds to our unique element in the singleton lambda, is just the natural module over the matrix algebra, which is just field to the power n. And this module has a standard basis, and that's exactly the basis which is used to define the cell module. And the above bilinear form gives us the usual bilinear form on k to the power n, where the standard basis is an orthonormal basis. So this follows from the fact that if we take two matrix units ei, s and et, j, then the outcome is ei, j with a coefficient delta s, t. So our psi st is equal to delta s, t. That's a Kronecker symbol delta, which gives us exactly that the standard basis of the cell module is an orthonormal basis. Here are some properties of the cell modules and the corresponding bilinear form. First of all, this form is symmetric. So phi lambda applied to x, y is equal to phi lambda applied to y, x for all x and y in the cell module W lambda. Proof: if we apply iota to our equation c upper lambda I, s, c upper lambda t, j equals psi s, t, c upper lambda I, j modulo a upper less than lambda. So if we apply iota to this equation, we will get c upper lambda j, t times c upper lambda s, I is equal to c upper lambda j, I with the same coefficient psi st, because iota is linear, modulo the same ideal. And now if you look at the definition, this means that psi s, t equals psi t, s, which means exactly that our form is symmetric. And the second property is that it is associative modulo our anti-automorphism lambda. This means that for any a in A and for all x, y in W of lambda, the value of phi upper lambda at the pair I of ax, y equals the value of phi upper lambda at x, ay. Proof: we look at the product c upper lambda I, s times a times c upper lambda t, j. By the associativity of our multiplication, we can compute this in two different ways. So we can bracket the last two factors first or the first two factors first. And also let us note that c upper lambda I, s times a is equal to iota applied to iota of a times c upper lambda s, I. And now we can simply write down both sides of our equation for the I associativity of our form and explicitly compute it using the definition and the coefficients r sub a, f, g, which are used to define the form, and compare. And the result just falls out. So our form phi upper lambda is both symmetric and associative. A consequence of this is that the kernel of phi upper lambda is a submodule of the cell module W of lambda. Indeed, take any element A in A and any element X in W of lambda and any element Y in the kernel of our form. Let us compute phi upper lambda at the pair X, ay. Using the associativity, we can move A from the second argument to the first argument, at the expense that we should take iota of A. But now still the second argument is in the kernel, so the total outcome will be 0. And this means exactly that ay is in the kernel of our form. So the kernel of our form is a submodule of the cell module. So we can take the quotient of W of lambda by the kernel of our form. If our form is 0, this quotient will be 0. But if our form is not 0, then we denote this quotient, this is a non-zero A module, we denote it by L of lambda. And the main theorem, which is a classification of simple A modules, is that the set of these L lambdas indexed by those elements lambda in lambda for which the form is non-zero, this set forms a full and irredundant set of representatives of the isomorphism classes of simple A modules. So let's prove it. Let us start by proving the simplicity of L lambda, provided that the form is non-zero. Take any element outside of the kernel of the form. So any element in the cell module outside of the kernel of the form. Then, since it's outside of the kernel of the form, the evaluation of the form at some CS and this element x is non-zero. But then if we look at the definition, this means that if we multiply ci, x upper lambda with x, the outcome will be a non-zero scalar multiple of ci. And this means then that all ci belong to the submodule generated by x. So the submodule generated by x is the whole cell module. But this means exactly that if we factor out the kernel of the form, then any element generates that quotient. So this quotient is a simple module, because it is non-zero. And finally, let's prove that any simple module is of the form L lambda. So let L be a simple A module. So by construction, the left regular A module has a filtration with cell subquotients. So with subquotients which are cell modules. So therefore L appears as a subquotient of some cell module. So let us choose a maximal lambda with respect to our partial order on lambda, such that L is a subquotient of the corresponding W of lambda. So if L is in the kernel of phi lambda, then the whole ideal A less than or equal to lambda annihilates L. And therefore this ideal does not contain any primitive idempotent which corresponds to the module L. But then L should appear as a subquotient of A modulo that ideal, and this contradicts our choice of lambda as the maximal element for which L appears in the corresponding cell module. And finally, of course, different modules in our list have different annihilators, more or less by construction, because the cell module is annihilated by the ideal, which is generated by all elements in the basis, which corresponds to elements in the lambda which are strictly smaller than the index of our cell module. So this proves the main theorem. Now let us try to give an alternative characterization of cellular algebras. Let A be a field and A a finite dimensional associative and unital K algebra. Let I be an involutive anti-automorphism of A. Definition: a two-sided ideal J of A is called a cell ideal, provided that it is stable under I, and there is a left ideal delta in J, and an AA bimodule isomorphism alpha from delta tensor over Ki of delta to J, which is compatible with iota in the following sense. When we apply iota to alpha of x tensor iota of y, the outcome should be equal to alpha of y tensor iota of x for all x and y in delta. For example, the algebra of all n times n matrices over K is a cell ideal of itself, with delta being the linear span of all matrix units of the form ei, 1, where I is between 1 and n, and alpha mapping the tensor product of ei, 1 with e1, j to ei, j. Now we can give an alternative characterization of cellular algebras, which is due to Koenig and Shi. So a pair A, I extends to a cellular algebra if and only if there is a vector space decomposition of A as a direct sum of subspaces U1, U2 and so on Um, such that each subspace Ui is stable under iota. If we take the direct sum of U1, U2 and all the way up to Ui for any I, we denote this direct sum by J sub I. This should be a two-sided ideal of A, and such that J sub I modulo J sub I minus 1 is a cell ideal of A modulo J sub I minus 1 for all I. So this theorem is proved in the paper by Koenig and Shi, which is called On the Structure of Cellular Algebras, which appeared in 1998. Here is an example. We consider the algebra k of x modulo x to the power n. We already know that it's a cellular algebra. Now we provide a description of the cellular algebra in view of the definition using cell ideals. So the iota, the anti-involution, is the identity map. This algebra is abelian. We define u sub I as the linear span of x to the power n minus I for I between 1 and n. Then, of course, iota of u sub I is equal to u sub I, and if we add up u1, u2 all the way up to ui, we get a two-sided ideal of A. The ideal ji modulo ji minus 1 is just the ideal which is generated by x to the power n minus 1 modulo ji minus 1, and we take as delta I the whole ideal ji modulo ji minus 1 inside A modulo ji minus 1. And now we can define our isomorphism alpha from delta I tensor delta I to ji modulo ji minus 1 by sending A times x to the power n minus I plus ji minus 1 tensor B times x to the power n minus I plus ji minus 1 to AB times x to the power n minus I plus ji minus 1. And then it's clear that the corresponding subquotient will be a cell ideal inside A modulo ji minus 1. Let us describe briefly some further properties of cellular algebras. First of all, finite direct sums of cellular algebras are cellular. And of course, finite tensor products of cellular algebras are cellular. If an algebra A is cellular, then A op is also cellular. And if characteristic of K is different from 2, then cellularity is a Morita invariant. That if we have some cellular algebra A and some algebra B which is Morita equivalent to A, then B is also cellular. Property 5. The Cartan matrix of a cellular algebra is symmetric and positive definite. Property 6. A cellular algebra is quasi-hereditary if and only if its Cartan matrix has determinant 1. And property 7. A cellular algebra is quasi-hereditary if and only if the form phi upper lambda is non-zero for all lambda. Let us dive into one more general example of symmetric groups. So the point is that the group algebra of the symmetric group over any field is cellular. So consider the symmetric group Sn on the elements 1, 2, and so on n. And let K be any field. Consider first the integral group algebra of Sn. It has a standard basis, which is indexed by elements in Sn, and it also has the Kazhdan-Lustig basis, which we denote by W underlined, where W is an element in Sn. So the definition of the Kazhdan-Lustig basis requires extending the setup from the symmetric group to the Hecke algebra, then defining the Kazhdan-Lustig basis there, and then specializing it back to the group algebra of the symmetric group. We will have an explicit example of S3 in a minute. And the Kazhdan-Lustig basis of the integral group algebra of Sn induces a Kazhdan-Lustig basis of the group algebra of Sn over any field. So we can use the Kazhdan-Lustig basis to define the so-called left, right, and two-sided Kazhdan-Lustig preorders and cells. And the two-sided Kazhdan-Lustig cells are indexed by partitions of n. And if we fix a partition of n, a partition lambda of n, then the left and right cells inside the corresponding two-sided cell are indexed by the standard Young tableaus of the shape lambda. And so the cell datum for the group algebra of Sn is thus given by the partially ordered set of all partitions of n with respect to the dominance order. I is the usual anti-involution which sends an element W to its inverse. M of lambda is the set of standard Young tableaus of shape lambda. And the image of our map C gives us the Kazhdan-Lustig basis of the group algebra of the symmetric group for the indexing provided by the Robinson-Shenstedt correspondence. So here is a detailed example of the group algebra of S3. So we consider the group S3, so that's a group of all permutations of 1, 2, and 3. It has 6 elements, and for simplicity we will write those elements in the Coxeter representation of S3. So S3 has the identity and then 2 Coxeter generators S and T, and then the remaining elements are ST, TS, and STS, which is equal to TST, and this is usually denoted by W0. And the Coxeter relations defined in S3 are S squared is the identity, T squared is the identity, and STS is equal to TST, which we can write at ST to the power 3 is the identity. The Kazhdan-Lusztig basis of the group algebra of S3 is given by the following elements. E underlined is E, S underlined is E plus S, T underlined is E plus T, ST underlined is E plus S plus T plus ST, TS underlined is E plus S plus T plus TS, and W0 underlined is just the sum of all group elements. And we can write the multiplication table in the Kazhdan-Lusztig basis. So here is the multiplication table in the integral group algebra of the symmetric group in the Kazhdan-Lusztig basis. So if you multiply x underline with y underline, this is the outcome. So E underlined is the identity, so nothing happens in the row 1 and in the column 1. And the remaining multiplications are quite complicated. So for example, T underlined times ST underlined is equal to T underlined plus W0 underlined, and so on. So one can compute all these multiplications, and here is the outcome. So we take as the partially ordered set capital lambda the set of all partitions of 3 with respect to the dominance order. So 1, 1, 1 is the smallest element, it's dominated by 2, 1, and that is dominated by 3. As M of the partition 3, we take the unique standard Young tableau of shape 3, which is just 1 to 3. As M of 2, 1, we have 2 standard Young tableaus of shape 2, 1. The first one is 1, 2, and 3, and the second one is 1, 3, and 2. And as M of 1, 1, 1, we have the unique standard Young tableau of shape 1, 1, 1, which is 1, then 2, and then 3. And here are the basis elements. So the basis elements which corresponds to 3 and the pair of the same standard Young tableau for that shape is E underlined. The basis element for 2, 1, for 1, 2, 3, 1, 2, 3 is S underlined. For 1, 3, 2, 1, 2, 3 it's TS underlined. For 1, 3, 2, 1, 3, 2 it's T underlined. And for 1, 2, 3 and 1, 3, 2 it's ST underlined. And the last basis element for 1, 1, 1 and the pair of the same tableau for this partition is W0 underlined. So here is a random check of the last axiom. The last axiom is non-trivial and requires a check. So if you multiply T underlined with S underlined from our table, T underlined times S underlined is TS underlined. So the coefficient here is 1. And this is in the same cell. And T underlined times ST underlined is T underlined plus W0 underlined, and the coefficient at T underlined is 1. And W0 underlined is in the smaller cell, so we can forget it. And we see that this coefficient 1 coincides with this coefficient 1. And another random check, so ST underlined times S underlined is S underlined plus W0 underlined. We have the coefficient 1 here. ST underlined times ST underlined is ST underlined plus 2W0 underlined. We have the coefficient 1 here. Again, they correspond. And finally, TS underlined times S underlined is 2TS underlined. And TS underlined times ST underlined is 2T underlined plus 2W0. So again, the coefficients coincide. So this is just a random check of our last axiom. And now let us discuss the cell modules. So the cell module which corresponds to the partition 3 has basis given by E underlined. It's killed by all elements W underlined different from E. And the corresponding bilinear form phi upper 3 is always non-zero because its evaluation at the basis elements gives us 1. And this is non-zero for any field. So this gives us the sign S3 module for any field. It always exists and it has this form. Next, the cell module for the partition 1, 1, 1. It has basis W0 underlined, and the evaluation of the form phi at the unique basis element is equal to 6. That's exactly this coefficient 6 here. And 6 might be non-zero, but it also might be 0. So 6 is 0 in characteristics 2 and 3. So this cell module gives us a simple module in characteristics different from 2 and 3. And this gives us the trivial S3 module outside the characteristics 2 and 3. And the characteristics 2 and 3, the cell module is not counted. So as we see, we have the sign module, which is always defined. Note that in characteristic 2, the sign module coincides with the trivial module. And we have the trivial module, which we now have in characteristics outside 2 and 3. So what happens in characteristics 3? Well, we also have the cell module W2, 1. It has basis S underline and TS underline, and the matrix of the corresponding bilinear form is 2, 1, 1, 2. So this matrix has determinant 3. So in particular, the form is non-degenerate outside characteristic 3, and in characteristic 3 the form is degenerate, but the matrix is non-zero, so the form is non-zero. Which means that this module, cell module, always gives us a simple module in all characteristics. But in characteristic 3, the form is degenerate, so the dimension of the corresponding simple module is 1. And this gives us the trivial module in characteristic 3. While outside characteristic 3, the form is non-degenerate, and we have the two-dimensional simple S3 module outside characteristic 3. And so this module L2, 1 is the trivial S3 module if the characteristic is 3. So this describes us simple modules for the group algebra of the symmetric group S3 in all characteristics. Okay, extra problems and questions at the end. The first one, prove that any commutative algebra is cellular. The second one, write down all details in the proof of property 2 of the bilinear form. The third one, prove the alternative characterization of cellular algebras by Koenig and Shin. Problem question 4, prove that finite direct sums of cellular algebras are cellular. And problem question 5, prove that any semisimple algebra over C is cellular. Thank you very much and see you next time.